Pure, second order differential equations 2, non-homogeneous case. Particular integrals of polynomial form. So just to recap the vital steps involved, we first solve the homogeneous second order differential equation to find the complementary function, and then we consider the non-homogeneous case in order to find a suitable particular integral. And together the complementary function and particular integral will give us the general solution. So here is a differential equation that we've seen previously. So looking at the homogeneous case first, we've written down the auxiliary equation which we've solved for m and has given us a complementary function. So just to remind you that if we only use the complementary function, then the differential equation would only equate to 0. So now we have to look at a way of getting the differential equation to equate to the right hand side, which is f of x. So from the complementary function we can now move on to the non-homogeneous case and looking at this f of x. We can see that f of x has a quadratic form, so we are going to try a trial function of the form y equals little ax squared plus bx plus c. So we're trying to get something that mimics this f of x on the right hand side, so we go for a complete quadratic form. Differentiating this trial function, we get dy by dx is 2ax plus b, and then differentiate again for the second derivative, we get 2a. Now we sub all of this, we're going to substitute y and its derivatives into the non-homogeneous differential equation. So starting with the second derivative, we need a second derivative minus a first derivative minus 2y, and we now need it to equate exactly to the right hand side, 3x squared plus 7x plus 1. So the key thing here is to take this non-homogeneous quadratic and try a function of quadratic form. Don't use capital A's and B's, use lowercase letters. Then we can use the first derivative and the second derivative to substitute them into the second order differential equation in the non-homogeneous case. So now we have this equation, we can start to look for the values of a, b and c, and a good way of doing this is to pull out the coefficients. It's called comparing coefficients. So if we start off with x squared, there's minus 2x squared there, 2ax squared I should say, so that's minus 2a, and on the right hand side there's 3x squared. So the minus 2a must be a match for the 3, which means that a must be minus 1.5. We can do a similar thing now for the terms in x. So there's minus 2ax, there's minus 2bx there, and there's 7x on the right hand side. So pulling out those coefficients, there's minus 2a minus 2b equals 7. And if we substitute for a, we can find that b is minus 2. If we now do a similar thing pulling out the constant terms, there's a 2a, a minus b, and a minus 2c, and that has to match the one on the right hand side. So pulling out the constant terms, that was a 2a minus b minus 2c has to match the one on the right hand side. And if we substitute now for a and b, we'll find the last constant c is minus 1, which gives us a particular integral which works, and it has the form y equals minus 1.5x squared minus 2x minus 1. And that's our particular integral for this problem. So this we found a by pulling out all the coefficients of x squared, or both of them in this case. Then we found b by looking at all the coefficients of x, and then we found c by looking at all the constant terms. And this particular integral will satisfy the non-homogeneous differential equation. So once you've found your complementary function for the homogeneous case and a suitable particular integral for the non-homogeneous case, then together you have a general solution for the original non-homogeneous differential equation. And we can now look at the effect that these unknown constants a and b have on the solution and characteristics of this general solution by looking at a GeoGebra file. So here we have our general solution at the bottom, and I've set a and b to the values of 1, and we have this red solution curve. It's worth noting, one thing we can note straight away is that the y-intercept when x is 0, the y-intercept is going to be the 2 plus the 1 minus the 1, or in other words a plus b minus 1. So at the moment the y-intercept is 2 plus 1 minus 1, which is at 2. So by changing a and b we can control the y-intercept, which is a plus b minus 1. Other things to note, if we consider large values of x first, so when x is a large number, this b e to the minus x will tend to 0, and the dominant term will be this a e to the 2x. The quadratic will be big, but it won't be as large as this dominating e to the 2x. So when we are looking at large values of x, we can see that the red solution is very close to this blue a e to the 2x solution for large positive values of x. When x is negative, then this e to the 2x term, that will be tiny, that will be very small, and the dominant term becomes this b e to the minus x. Remember x, we're talking about a negative x. So when x is negative, we can see that the solution stays close to this dominant b e to the minus x term. So if we now set b to 0, then when b is 0, so this term has completely disappeared and x is still negative, so this term is tiny when x is negative, and what happens now is that the solution behaves much more like minus 1.5x squared. That term has disappeared, this term's tiny, and you get a different dominant term. So by varying a and b we can look at different solutions to the problem. So if the non-homogeneous right-hand side is a linear function, we would try y equals little ax to the little b, and if the right-hand side is a polynomial of order n, then we need to try a complete polynomial of order n in order to find a suitable particular integral. So in the next video we're going to be looking at particular integrals with trigonometric functions.